So today I want to use what I explained last time to well, go a little further and explain the relation with some representation theory, and then vector bundles, and suggest a few geometric applications. So let me remind you, so what was the main result last time? So we started with a reductive group over an algebraically closed field. Let's say characteristic 0 to be safe. And then we had this Borel subgroup and this maximal tori. And so the result was a classification of parabolic subgroups. And so we proved that in each conjugacy class there is a unique parabolic subgroup containing a fixed Borel B. And then this P was defined by, remember, a set of simple roots. Okay, so we had the notation was like this. So we had the root system, the positive roots, inside phi plus we had the indecomposable roots, which are called simple. Okay, and then we had the Weil group. So to each root alpha, we mentioned that there was some simple reflection given by this kind of expression. And so the Weil group, which is the normalizer of the torus modulo the torus, is the finite group generated by all these simple reflection, and it is enough to take alpha simple roots. This gives you a minimal system of generators. Okay? And then, so the classification of parabolics was like that. So you choose some subset I of delta, and then the subgroup of the Weil group generated by the corresponding simple reflections. And so there is a corresponding group, which is which you can define like this: group generated by B and the Weil group, and the subset of the Weil group generated by I. Okay, so we saw that essentially this is the group generated by B, and remember there was these root subgroups. For each root there is a root subgroup whose Lie algebra is the root space in the Lie algebra. So B corresponds to the positive roots. And then Pi in its Lie algebra will include some negative roots, and there are those that are combinations of roots in I. Okay, so this is the group generated by B, and the roots subgroups generated by the opposite of the simple roots in I. Okay, so I need to remind you of some notation to explain a bit the structure of this group, and then we will forget about it. So what I want to stress is that so when you look at the level of Lie algebra, okay, so remember that G was the could be decomposed as the sum of the Lie algebra of the torus plus the root spaces, one-dimensional, corresponding to the roots. And so since Pi is normalized by the torus, it has a decomposition of the same type. So it will be T plus certain root spaces. So what are those? Well, we have B, of course. So all the positive roots. And then we have some negative roots. And the negative roots that you get are exactly because of this, those that are combinations of the simple roots in I. So I will write maybe like this. Okay, so combinations of simple roots. So I mean with non-negative coefficients in your subset I. So you have, again, all the positive roots, and then you allow only the negative roots that are combinations of your simple subset, your subset of simple roots. Okay, so maybe an example with GL. Just to see what happens. So maybe you can observe that there is a, yes. Okay, let's try this. So there are really two types of roots. Those here that appear beta. You have minus beta here and beta somewhere here. And so you have two kinds of roots, those which are linear combinations of those simple roots such that they appear both with their opposite, and those they do not. So this gives you a decomposition of Pi as Li plus Ni. So with the following, so Li again is made of those roots that appear with their opposites, so those that are combinations of simple roots in I. And the remaining set of root spaces is the positive roots that are not in this subset. Okay, so this means that beta, remember beta is some, can always be decomposed as a linear combination of these simple roots. So it means that, so you have, it means there is a positive coefficient on a root which is not in I. So when you when you conjugate by some root space here, you will add some root alpha, which has 0 coefficient outside I. So this property of having a positive coefficient somewhere outside I will remain true, which means that Ni is normalized by Li. In fact, Ni is normalized by the whole of Ni. Yeah, so I wanted to give the example of GLN. So in torus is here, the positive roots giving beta, giving B are the correspond to the entries above the diagonal. And then you choose some simple roots here. So this means you allow some combinations that will generate blocks here, sub-blocks. Okay, so here you still have 0. Here you have the negative root spaces that are allowed here. Okay, and those negative root spaces, they have their corresponding positive root space on the other side. So this generates this subalgebra. Okay, so Li is the sum of these diagonal blocks, and Ni corresponds to what remains over the block diagonal. Okay, that's the idea. So what I claim is that, well, it's better maybe to state things at the level of groups. So we know we can go to the Lie algebra to the group using the root spaces. So there is so at the group level, we have a subgroup Li, which is generated by B, not B, by T, and the U plus or minus alpha, it's like the U alpha for alpha in this alpha I. That will be the product of the matrix groups corresponding to these blocks. And we have the UI generated by the other root spaces. Okay, so it will be the unipotent group with one on the diagonals and some entries in this shaded area. Okay, so then the facts are that, well, Pi is the product of this or these two groups. And actually, UI is the unipotent radical. You can describe the radical. This is so it contains UI, and there is something more, which is the center of Li. And the center is contained in the torus. So you see, in this case, what would be the center? It would be the space of matrices which are homothéses on each block. So you can describe it as the intersection of the kernel of the roots in I, and take the connected component. Okay, so this is the radical, and this means that when you quotient out by the radical, you get a semi-simple group. Okay, so maybe I should say that Li is reductive. With maximal torus, it contains T, so T must be a maximal torus in Li. And the root system is easy to describe because we started from the root system of G, and we just suppressed the roots that are not in I. So the root system is exactly given by this set of roots, which are combinations of the simple roots that you chose. Okay, so this is called the Lavie decomposition. So what is nice here is that you have a completely explicit description of, in terms of roots, of this unipotent part, which you can think of not so important, and then the reductive part, and which has a completely explicit root system. You just suppress part of the simple roots and keep what remains. Okay. So essentially, we know we have a very precise description of these groups, hence of the projective homogeneous varieties. So that was the goal of all this, to describe the homogeneous projective varieties, which are the G mod pi. Remember? So just a word of caution. This is that G mod pi as an algebraic variety does not necessarily determine G. Okay, you have an action of G on this variety, of course, but the automorphism group may be different. Okay, so be aware that sometimes, maybe I should erase, sometimes the automorphism group is bigger . Even the connected component, I mean. So sometimes G is really smaller than the automorphism group of G mod pi, even connected. Okay. If you want an example, you take a projective space of odd dimension, that's the simplest example, and then you notice that there is a transitive action of the symplectic group, and of course the symplectic group is not the full automorphism group of the projective space. So sometimes this kind of thing happens, but well. Okay, so the first kind of applications I would like to discuss is the application to representations. So we already mean this. So that's a linear action on the finite dimensional vector space. And so how to approach this? So there is you can do two remarks which boil down more or less to the same thing, but you can take the projectivization and then the action of G. You know that if you restrict it to B by the Borel fixed point theorem, there is a fixed point. Or we have seen by the Lee-Kolchin theorem, we can diagonalize the action of V. But so let's call this fixed thing point, so the line generated by some vector V, and then you see that the orbit of this vector is well, the stabilizer is a parabolic subgroup, so the orbit will be isomorphic to some G mod P inside P of V. And so you can look at the linear span. Inside this. And okay, so it tells you that if V is supposed to be irreducible, then any, by definition, this means that any subspace which is fixed by the group is either zero or the full space. So this must be an equality. So essentially, you can think of irreducible representations as generated in some way by homogeneous spaces in their linear embeddings. Okay. So to describe things more in more detail, you can take T a maximal torus, and then look at the action of T on V, and do the same as what we did on for the Lie algebra, that is, diagonalize the action. It can be diagonalized. So again, we have a decomposition, which will be a direct sum of some V mu. Mu is in the, remember, the character group. Homomorphisms from T to the multiplicative group. Okay. And V mu is a subspace on which T acts by multiplication by mu of T. And of course, we have that if you look at the action of G alpha on V mu, well, it goes to mu plus alpha. So those V mu which are non-zero, the mu that appears here with non-zero contribution are called the weight spaces. So the mu are called the weights. And of course, there is a finite number of weights, so you see that there exists lambda, let's say, such that a weight, such that lambda plus alpha is no longer a weight when alpha is a positive root. Okay, positive roots push weights in the positive direction, so by finiteness there is at least one maximal element, and then this means that it will be killed by all the positive root spaces. So it will be stabilized by B, and so we recover this fixed point here. So this is called the highest weight vector. And the corresponding weight is the highest weight. And the observation is that this completely classifies the irreducible representation. Okay, so this is highest weight. So fact. So one highly non-trivial fact is that if G is reductive, then the category of representation is semi-simple. So in other words, every representation is a sum, direct sum of irreducible representations. So it's enough to classify the irreducible representations. Two representations which are irreducible. I forgot to mention something, which is that now. So suppose we have a V, which is a V lambda, the highest weight. Okay, so again, the line generated by this vector is stabilized by B. So then when we take the orbit of G, we can forget about B, of course. So what remains are the negative root spaces, the negative root groups. So this linear span of G mod P will be generated by the image of V lambda by the negative root groups, which are at the level of Lie algebra. You can express it as the following. We just take V lambda and then we apply the negative root spaces in all possible ways. And then this will generate exactly this linear span. And this is and so it is easy to see that this is really irreducible. And you see that the weight here is lambda minus alpha 1 minus alpha k. So it tells you that all the weights in the representation generated by V lambda are of this form, so are smaller than lambda. And there is a unique one of weight lambda, which is exactly V lambda. So V lambda is the really the line generated by your vector space, your highest weight vector. Sorry. So then, now when you have two irreducible representations with the same highest weight, they must be isomorphic. Okay, so it was 2 V prime irreducible plus same highest weight. Then they are isomorphic. Okay, because you take two highest weight vector, V and V prime. Then you look at the vector, let's say U, called VV prime inside the direct sum. So this is again a vector of highest weight, the same one. Let's call it lambda. So it's still stabilized by B, and the weight is lambda. Okay, so it generates an irreducible representation U inside V plus V prime. And now you look to the projections to V and V prime. So they are non-zero because U is mapped to V or V prime. And then when you have a non-zero morphism between irreducible representation, so you know by the Schur lemma that there are isomorphisms. Okay, the kernel and image are sub-representations, so they should be either zero or everything. Okay. So we know that irreducibles are classified by their highest weight. And then it is not true that any weight corresponds to an irreducible representation. So there is a criterion for this. So for lambda, weight, so this is a fact, there exists V lambda of highest weight lambda. If and only if. So remember these co-roots that I introduced last time. The pair is with the weights, and the condition is that this is positive for any simple root. Okay, so we have a full combinatorial classification of irreducible module of a reductive group by the highest weights. Yes, sorry, this is not completely correct. This should be integers, non-negative integers. There is a positivity condition and an integrality condition. Okay, so in particular, you see that some lambda will play a special role. There are those that correspond to the dual basis to the simple co-roots. Okay, so if I denote by alpha 1, alpha r, the simple roots, there exists omega 1, omega r, such that you get either 1 or 0. And so these are called the fundamental weights. And so we have some representations which are called the fundamental representations. And if I come back to the description, sorry, what I insisted on at the beginning was that you could think of representations as giving you the linear embeddings of a homogeneous space, of projective homogeneous, rational homogeneous spaces. So if you look at P projectivization of this, and look at the orbit of a highest weight vector, this will give you what I denoted by G mod Qi, so the minimal G homogeneous spaces. Okay, so in a sense, so I will make this more precise later. You can recover all the representations by starting from these G spaces and looking at their minimal linear embeddings. Of course, the example is for again for GLN. Well, the fundamental representations are so there is the natural action on the n-dimensional space, and the fundamental representation is are the wedge powers of those. And so G of Qi is the Grassmannian of I-dimensional subspaces of V, and it's embedded in the representation by the Plucker embedding. Okay, so you recover this strong relation between the representation theory and the geometry of the homogeneous varieties. Okay, so now it's really possible to really construct the representations starting from the homogeneous spaces. So for this I need to talk about homogeneous bundles. Maybe some questions at this point? So homogeneous vector bundles that are not homogeneous, but they are vector bundles on homogeneous varieties with an action which is compatible with the action on the base. Okay, so the definition is that take a vector bundle. So an algebraic vector bundle. And you require that there is an action of G which is compatible with the action on the base. So the observation is that here when we write G mod P, there is a base point, P mod P. Let's call this X node. And then, so the stabilizer of X node is P. So by definition, the P will stabilize the fiber over X node. So let's call M this fiber. Okay, then there is an action of P. So linear action of P, a P module. And this goes on the other direction. Okay, we can recover E from just from M by the construction is like this. So there is this notation, which means that we take the product of G by M and we mod up by the relation, which is that if we multiply an element of the group by P on the right, this is equivalent to multiplying by P on the left on the P module. Okay, so we mod up by this relation, and it's an exercise to check that you recover your bundle. An important example will be when you start from, let's say, V, a G module. And so you consider it as a P module just by restricting the action. And the claim is that there is the corresponding bundle is really trivial as a bundle, as a G bundle on G mod P. And you check this by using the map. And using this map, you see that it is compatible with the relation by which you mod out. So it will descend to a map from this to this, and you easily check that this is an isomorphism. Okay. So indeed, the conclusion is that we have an equivalence of a category between vector bundles. Sorry, homogeneous vector bundles on G mod P and P modules. But of course, beware that P is not semi-simple or reductive, so its category of modules is more complicated. Particularly, it is not semi-simple. So homogeneous bundles will not decompose into irreducible in general. Okay, maybe the simplest example is you take G mod P to be one of the Grassmannians. And so that's the GLN mod this parabolic. And so you can look at V. There is an action of G on V, which gives you this trivial bundle. But it is not irreducible or a sum of irreducible. Just because there is the tautological bundle. Okay, corresponding to this representation here. There is a submodule stabilized by P, the one generated by the first I columns. And this defines the tautological bundle, which is a subbundle of V, of the trivial bundle. Maybe I should denote it like this. And there is a quotient bundle corresponding to this block. Okay, so here we have a trivial bundle, but although it is trivial, it is not a sum of irreducibles. So of course you have more complicated examples of this kind of phenomenon. But you have to keep this in mind. Still, there is a nice way to decompose any homogeneous vector bundle because of what I explained at the beginning with this Levy decomposition. Okay, so remember the Levy decomposition. Which was that P could be decomposed into L, which was a reductive group, and the unipotent part. Okay, so I use slightly different notations. I don't have the I that I had at the beginning, but doesn't matter. And so, since this is unipotent, when we have an action, a P module, we know that we can triangularize the action of the unipotent part, and it will have ones on the diagonal. So in particular, there is one fixed vector. So for any M P module, we can define M0 to be the set of vectors on which the unipotent part acts trivially. And as I said, this is non-zero. Okay? But now this is much nicer because the action here of PU is killed by definition. So what remains is in fact the action of L, which is reductive. So we just need to understand the structure of M as an L module, and since L is reductive, we know how to do that. We can decompose into reducible and classify by and classify by highest weight and so on. So we exactly know what happens. And then we can mod out N by M node and apply the same observation. So we see that there is actually a filtration, a canonical filtration. Such that the unipotent acts trivially on the quotients. Okay, so this is essentially an L module. So in particular, it will be completely reducible since L is reductive. And the corresponding vector bundles are also called completely reducible. So they are the easiest one to understand. So we know exactly what are the completely reducible modules. And from this, we know that any P module is obtained by extensions. This is what we don't understand. Extensions of the completely reducible modules. So yes. So conversely, we can take any L module. Suppose that M lambda is an irreducible L module. Then we can, of course, upgrade it to a P module just by saying that the action of the unipotent must be trivial. So here, remember we had some conditions to have an irreducible module with a given weight. We had essentially positivity, integrality, and positivity conditions. And these conditions are expressed not exactly in the same way because remember they were expressed with respect to the co-roots. And at the level of G, we take all the co-roots. At the level of L, we only take the co-roots that appear in this subset I. Okay, so here this is defined for we had this positivity condition. So we always need the integrality condition, and the positivity condition is required only for alpha in I. If P is the parabolic corresponding to I, as we described it at the beginning. So, of course, not every P module will be of this type. But if you take a P module of rank 1, then necessarily the action of the unipotent is trivial, so it is irreducible. Okay, so special case. Dimension 1. So we get a line bundle, actually. If we want to think of N lambda on G mod P. And so lambda must be such that well, you see, L, remember, has a center plus a semi-simple part. A semi-simple group has no non-trivial character. So lambda must, for M lambda to be one-dimensional, lambda must restrict to 0 on the semi-simple part of L, which means that alpha check lambda is 0 for all alpha in I. This gives you the line bundle. So you see that, oh yes, I did not mention that. In fact, this gives you all the homogeneous line bundles. But in fact, it's not difficult to prove that any line bundle on G mod P is actually homogeneous. You can, for example, because remember we had these Breuer decompositions, which told us that we have a, remember G mod P was made of a big cell, and then we had some hypersurfaces, which are again compactifications of affine cells. Okay, so you have a cell decomposition, so it follows that the Picard group, the group of line bundles, the group of divisors, will be generated by those irreducible hypersurfaces, and by construction they correspond to orbits, so they correspond to homogeneous bundles. So that's a way to see that. So you see that the Picard group of G mod P the sum of the set of homogeneous line bundles. So it's exactly given by the weights lambda satisfying these conditions. So it's Z. It's the orthogonal to, it's given by cardinal of I conditions, so it is like this. Okay, and maybe more satisfactory would be that it is generated by the L omega I for I not in I. Okay, the fundamental weights give you minimal ways satisfying those conditions, and so they generate the Picard, they give you a basis of the Picard. Sure.
All these reducible dividers are not G invariant.
Not G invariant, no.
But the line bundles they are G equivalent.
Yes. They're not G invariant. They are B invariant.
Yes.
Yes. Or P invariance. So that's what you use to say they correspond to homogeneous bundle. They're not G invariant. They are G equivariant. So they're given by P modules. So now that we have a vector bundle, so it's natural to look at sections. So you know that when you have a bundle on a variety, the space of sections is the maps from X to E that inverse the projection. So that's a vector space. Of finite dimension if X is projective. So here the Borel-Weil theorem tells you exactly so what you get when you start from these irreducible P modules M lambda. So irreducible P L or P module. So they give you a vector bundle, homogeneous vector bundle E lambda. And the statement is that the space of sections of E lambda on G mod P is essentially V lambda. So for V lambda to be non-zero, you need the positivity conditions. And if they are not fulfilled, you get 0. Okay. So a special case would be that if you take G mod B and you take L lambda, so then you get the same statement. So it tells you that in order to construct the irreducible representations of G, you just need to know G mod B, the line bundles on G mod B, so that's the characters of B, so that's easy. And then take the space of global sections and you get your irreducible representations. So of course there are other ways to construct the irreducible representations, but this one is so it's really efficient, and it really gives you some geometric insight on the representation, which may be quite useful in a number of situations. So I will not give the proof, but maybe just a sample of it. An important ingredient is that let's denote by V this space of sections. I just want to well, actually, if you know how to, if you can prove this part follows quite formally. So let's consider only this space, section of line bundles on G mod B. And so there is this action of G. And so you want to think of weight vectors. When you have representations, first thing you try to understand are the highest weight vectors. And saying that it is irreducible means that there is a unique highest weight vector. So let's suppose there are two highest weight vectors. So maybe U and or S mu and S nu, highest weight vectors. Of weight mu and nu. Well, then you say that two sections of line bundles, they differ by a rational function. Okay, there are over each point you have two elements in a one-dimensional vector, and so they are multiple one of each other up to a well-defined scalar. So you can consider the quotient S mu S nu. This is a rational function on G mod B. And if we multiply by some element of B, so since they are highest weight vector, we will get mu of B divided by nu of B f of x. Okay. So in particular, if I take B in the unipotent part, the characters give me 1, and I simply get this relation. So my rational function is constant on the orbits of the unipotent parts. But in fact, you know that if you think a little bit about the Breuer decomposition, so remember we had this big open cell, which was a dense B orbit. If you think a little bit, you see that it is not only a B orbit, but a BU. BU orbit is actually dense. Okay, so here there is a dense BU orbit. So then, since F is a constant on this orbit, on a dense orbit, it must be constant. Okay. So this implies, when you use the previous relation, this implies that mu equals nu, and that as mu is just a multiple. S mu is a multiple of S nu by a constant. Okay, so we have proved that V is irreducible. So of course, what requires a bit of more work is to prove that this is non-zero. Well, you can check the weight is lambda. This is not difficult, but let's check is this not zero under the conditions that you expect. Okay, but at least from the Breuer decomposition, you see that it must be irreducible. Question? So one consequence of the statement is that if you look at L lambda line bundle on G mod B with lambda so dominant, this is the word for expressing the positivity condition, then it has lots of sections. Consequence. So L lambda on G mod B for a lambda dominant, so which means that these positivity conditions are fulfilled. So it has lots of sections. And in fact, it is what is called generated by global sections. Which means that for any point, you can find a section that does not vanish at this point. Okay. Well, in this case, this is rather obvious because suppose that this is not true. So there is a point at which all sections vanish. But then by homogeneity, all sections will vanish at all points. Contradiction. Something slightly stronger, so a different statement, is that if, suppose that the conditions are strict, so let's state it for line bundle on G mod P. So then the condition, the positivity condition. So we have for this we need so these are the conditions that express that we have a line bundle, and suppose that the other positivity conditions are strict. Then this bundle is ample, and even very ample. Which means that space, it defines very ample, means that the space of sections define an embedding of the overriding into the projective space. And what is the embedding? Of course, you guess that it is the embeddings inside the lambda dual. Okay. So in particular, you see that, oh yes, I could have defined, so there is a special P module which is the Lie algebra, the adjoint action. Oh, there is also the full Lie algebra G by restricting the adjoint action of G. Or you can, take the quotient. And what is the corresponding homogeneous vector bundle to this P module? What is it? Just the tangent bundle. Okay. The fiber at the base point of the tangent bundle of G mod P is the quotient of the two tangent spaces to G and P, which is exactly G mod P. Okay, so this is, and well, it is the case that in most situations, this homogeneous vector bundle is not irreducible or completely irreducible. Okay, this happens, for example, for Grace-Minions, but in general, it is definitely not true. But still, what you can do is you can analyze. So you know that an important object is the determinant of this tangent bundle. So the determinant of G mod P is a line bundle. So this is a one-dimensional representation. So it gives you a line bundle, which is the determinant of the tangent bundle of G mod P. So the anticanonical line bundle. Okay. So from this, you can compute quite explicitly the. So this will be L mu. So you can compute quite explicitly the mu that defines this anticanonical bundle. And you usually see that it verifies the condition. So in particular, this is very ample, which means that all G mod P are examples of Fano varieties. Okay, so there are good, interesting geometric objects in their own. They give you interesting varieties with this property to be Fano. You can construct many other Fano varieties from these. And you can also study many interesting varieties using those and homogeneous bundles on these varieties. So I want to give you a few examples. They're just starting points for deeper research, but just to show you a few directions. There is a nice situation that is met quite often, which is that when you have a P module, which is a submodule of a G module. You can start from a G module, and you restrict the action to a parabolic subgroup. It is no longer irreducible in general, of course. And so you can ask what are the P submodules and what you can do with that. So what are my notations? Yes. So I will have M inside V. So this is a G module, and M is a P submodule. Then, of course, we have the corresponding vector bundles, and the inclusion will remain true. We have E like this, which will be a subbundle of, let's call it F. And remember that this one is trivial. Okay. So this is a vector bundle on G mod P. This one has a projection, of course, to G mod P, but now since it is trivial, there is projection to V. Let me call this pi. And so it's natural to consider the projection of E to V. And I call X the image. Okay, so X is P of E. So you see that this map is the projection from this product, and G mod P is a projective. So this is a proper map. So this map P will be proper, so the image of E is closed inside V. And of course, everything is compatible with the G action, so X is stabilized by the group. Okay, so let's be more precise, and I'll give you some example in which this situation appears. So maybe example 0. You start from Pn and take the line bundle O minus 1. Okay, so parameterizing lines. Okay, so this is a subspace of Pn times An plus 1 and projection to An plus 1. What is this? So here we have a vector, here we have a line. This is the line generated by the vector, except if the vector is 0 here. So as you probably know, this is the blow up of the origin. So extremely simple example, but you see that it is birational, gives you a natural birational map. And it will occur in many situations that P is really birational. And this will be very interesting if you care about birational geometry. So, slightly more sophisticated example. Maybe I should erase this. So we take the so V B vector space of dimension n. So we look at the Grossmanian GRV. So remember that we have the tautological and quotient vector bundle. And here I look at the vector bundle, which is the homomorphisms from V to T. Okay, so which is a subbundle of the trivial bundle homomorphisms from V to V. Space of endomorphisms. Okay, so I have my map P here, which gives me something inside this, and what it is. What is it? Well, you see that if you have something here, this is a map from V to T, seen as a subspace of V. So this is just a linear map, but with the property that the image has dimension, at most, the dimension of T, which is R. Okay, so you will get, in fact, the image will be XR. So space of endomorphisms of rank at most R. And in this case, this is birational, because in general, T must be the image And so if you have something which has exactly rank R here, the point corresponding here must be its image, and there is a unique way to put it here. Okay? So of course you can characterize matrices of rank at most R by saying that the image is dimension at most R, but you can say that the kernel has a dimension at least n minus R. Okay, so there is something similar on the other side. You take spaces of dimension n minus R, and so here you have let's say tautological and bundle T prime Q prime, and saying that a map has kernel containing T prime means that it factorizes through the quotient. So it's natural to look at this space here, and again we have a birational map on the other side. Okay. So you see that not only we have a nice resolution of singularities of these varieties, this variety. This is a singular variety, which will become singular when the rank drops to at least R minus 1. So singular object, but which has a very nice resolution of singularities by something which is very simple, just a vector bundle over a gross median. And here's the nice ingredient is that we have two natural ways to do that. And so there will be a birational isomorphism between these two smooth varieties, and this is called a Mukai flop. So what's the point with that? So we see that we have a very nice birational maps between smooth varieties, but we have also nice resolution of singularities of some important objects. And from this we can try, for example, to understand the equations of this variety and so on. And this is very important. This gives, if you go to the relative setting, you have all the determinantal varieties, which are a very important subject. And this is really essential in the study of these geometric objects. Another situation of the same type. So example 2. Good. So now G will be any simple algebra, say. And so I want to consider G mod B. So I have the adjoint action of on B, and remember it stabilizes BU, the unipotent part. And so I have the tangent bundle G mod B. And if I'm interested in the cotangent bundle, you see that well, the dual to a quotient is just the orthogonal to B. And then, when you, in the case where G is simple, you have the natural quadratic form, which is fundamental, but that I did not mention, which is the Cartan killing form. That you can analyze to verify that the orthogonal to B is precisely BU. Okay, which is of course embedded in G. So the bundle corresponding to this representation of B is of course the cotangent bundle. And that construction gives us a map to G. And the image is denoted by N. So what you can prove is that N is what is called the nilpotent cone. It is the variety of all nilpotent elements in the Lie algebra. So this situation is very nice for several reasons. So first, it is for any Lie algebra, it's a birational. So P is always birational. It is called the Springer resolution. So N is a singular object, as before. So of course it is stable on the G, and there is this nice property that there are only finitely many orbits. Okay, you know that for GLN, nilpotent is for some Jordan decompositions. Nilpotent matrices, they are described by the size of their Jordan blocks, and the size of the Jordan blocks are just integers. So you have, they are classified by partitions. So there is finitely many orbits. And here you have the fact that the bundle that gives you a resolution of singularity is the cotangent bundle. And the cotangent bundle has this special property that certainly Misha mentioned and discussed quite thoroughly, that there is a symplectic structure. And P preserves the symplectic structure. There is also a natural structure on the nilpotent cone, which is the Koston-Kirillov structure. And P is a symplectic resolution. So you can do the same by replacing G mod B by some G mod P. If you take the cotangent bundle of G mod P, so again the corresponding P module is the dual to the quotient of G by P, which again is the orthogonal to P, which again is the unipotent part of P. Inside G. And so what you get is the image will be some closed subset of G. And since this is contained in the what I erased in the unipotent part of B, you get inside the nilpotent cone. So you get something which is stable under the group inside the nilpotent cone, and since there are only finitely many orbits, you must get the closure of one orbit. Okay, so the image is the closure of a certain nilpotent orbit. So there are bad news and good news here. Bad news are that these maps are no longer always birational. It may happen that they are not. In general, they are, but there are a few exceptions. And the good news is that you can find different G mod P's which give you the same orbit closure here. So it gives you, again, interesting birational morphisms between different varieties. Okay. When it's not birational like that, no, you have to go to... So it's always birational if you take GLN. I think if you take probably just the projective space with the symplectic, with the action of the symplectic group, as I mentioned before, the index would be 2. I'm not sure. The degree should be 2. And I just want to finish with a simple example of what can be done with rank 2 groups. Rank 2 simple groups. So I didn't mention Dynkin diagrams, but they are classified by there are 3 irreducible Dynkin diagrams of rank 2. Okay, so this one corresponds to A2. This is essentially SL3. This one is either B2 or C2, which means SO5 or SP4. And here we have so G2, which corresponds to the exceptional Lie algebra G2, for those who know about that. And remember, since we are in rank 2, we have exactly 4 homogeneous spaces. One is a point, so we can forget about it. So, but we have G mod B, and then we have G mod P1 and G mod P2. The 2 generalized Grossmanian and 1 full flag variety. And remember, I did mention that these 2 projections are just P1 bundles. Okay, so oh yes, so for what is it for A2? For A2, you just get P2 and P2 dual, and here the full flag variety. And for the 2 other groups, so let's think in terms of SP4 for the second example. So as I mentioned before, we have an action of P3, transitive action of SP4 and P3, which must be one of the generalized Grossmanians. And the other one is a space of 2 planes in 4 space that are isotropic. So it is a variety of G24s, Grossmanian G24. You know that G24 is a quadric, dimension 4. And in fact, the other homogeneous space of SP4 is a 3-dimensional quadric. And we have 2 projections with, let's call SP4 mod B. And for G2, well, there is one generalized Grossmanian of G2, which is just a quadric of dimension 5. So we found again one of those examples where the automorphism group is not the group from which you started. The automorphism group is whether a PSO 7. And on the other side, so there is one representation which is just a 7-dimensional representation, because G2 is containing SO7. And the other irreducible representation is the adjoint one. So we have another variety of the same dimension, must be of the same dimension, inside the projectivization of G2. Okay, and so, sorry?
What is G2?
This is the Lie algebra. So this is this is an irreducible representation. So I take it projectivization. There is a unique closed orbit, which must be a generalized Grassmannian, and this is this variety. Okay, so now just look at this. Projections. So I said that if you have a line bundle here, let's call it P. You can look at the push forward here, and I said that there is a natural map from the dual here to the dual of the push forward of the dual. So a second. What is this? This is a space of sections over fibers. So here I take a point and I evaluate a point on a section. So this gives me this map. There's a natural map here. So suppose that the fiber is just O of 1. Is O of minus is O of minus 1, yes. Oh, sorry. This. Suppose that when you restrict to the fibers of this map, we just have O of 1. Then on the fibers, you see that we have a map. If I restrict to the fiber, I have just the total space of O minus 1 over P1. And I'm mapping this to A2. So this is exactly my example 0. So this is birational. Okay, so this map is birational fiber by fiber. So it is globally birational. Okay. So I can apply this observation to my diagrams here. So you see that if I start from G mod B, I can find a bundle which has degree 1 on each of the two fibers, and so I can push to two vector bundles on the two generalized Grassmannians. Okay. And by what we just observed, you see that the total space of this line bundle is birational to the total space of this rank 2 vector bundle, and birational to the total space of this rank 2 bundle on this other generalized Grassmannian. So there is a birationality here. Okay, and these were studied quite recently by Ed Ziegel for C2B2. So for A2, this is just essentially the Mukai flop, and by so Sasha and an Asian team, I don't remember the names, Miura and other people. In the case of G2, and essentially the result is that these two spaces are derived equivalent. Okay, so that you can. So from this, that's an example of what you can do with these homogeneous vector bundles. In this case, construct interesting birational maps with very nice and exceptional properties. So probably it's time that I stop. If you have questions, of course.
This is the last lecture, so you have
last chance.
You have the last chance. Certainly, then you can send some question by email.
Sure.
If you would like to put some question now. Do you have a question? If not, the course of Laurent Manivel is finished.